Now, in this section we are going to look at pressure as the quantity, and we will see how we can look at the hydrostatic pressure. Hydrostatic pressure essentially is in a phase that we are looking at here, which is liquid like, and that is why we are looking at the hydrostatic pressure in a liquid phase of a pure substance, and then we are going to see how it is being calculated. For this particular reason, we have number density which is 0.556, and this simulation is called pressure in your SMD simulation box. Now, we have rigid container right now, reflecting walls. Then we are going to look at this particular liquid and understand the hydrostatic pressure. If you look at, you have temperature and particle of the mass is also there. We can vary these and see how does that affect the pressure calculations. And we know from previous we have to use VMDL coefficient for the calculation of pressure. Let us start now on your screen. We are looking at the equilibration. Let us look at averages. Excuse me. Now, in this case we have let us look at also real units, and we are at with the heat bath. So, temperature is constant, we want to look at the pressure. So, if you look at this reflecting wall, and there is we are going to now look at the pressure. So, now you are looking at a particular place in the pressure. So, if you look at pressure here is it's about 8.12 megapascals. So, you are looking at higher pressures in this system. So, now if you stop this location, and then we are going to change and see how the pressure changes with temperature. So, we increase the pressure. Now, let us look at the pressure value. So, it has gone up 1.24, and the temperature is gone up to 66 degrees. And so, let it run for a while, so that it can reach equilibrium state, and because it is heat bath, it will be at constant temperature. So, let us look at the temperature. It's constant, kinetic energy is constant, energy you are looking at potential and kinetic energy is constant. Now, number density, there will be some fluctuation of the velocity distribution. Now, you can see the spread of velocity distribution, which is Boltzmann distribution. Based on that, which is the configurational part, you are able to calculate the pressure 2.31 megapascals. Now, we are going to change, in fact, it is 2.39 pascals, sorry. So, now we are going to look at again and change the temperature and see what happens to the curve, which is Boltzmann curve here. Let us stop pressure here and then increase to almost 2.7. Now, you saw the Boltzmann distribution widening of the curve, because now more particles are feeling different kinds of velocity distribution. So, if I look at the spectrum of relative kinetic energy, you can see this lot of change in the colors, because there is big distribution of velocities here. But the point here is that now we are able to look at the pressure, which has gone to 3.74 pascals. Okay. So, with the temperature we are increasing the pressure, and the pressure is we are able to calculate that for this system of 200 particles using the theorem. So, now we are going to follow again, take another step on the temperature and see if we can see the broadening of the Boltzmann curve, which gives you the kinetic part, and then there is a configurational part. So, you saw the broadening of that. Now, you can see that pressure has also gone to 4.7 pascals. Now, let us create another situation where we are going to stop this simulation and put some external pressure and see how we can deal with the situation with the piston. So, we are looking at a very unit mass and unit pressure from outside, and see what is happening with the velocity distribution function in this case. So, now if you look at here, see piston moves upwards. So, because of the pressure, the piston is moving upwards. So, if you want to create external pressure, then we have to increase the pressure here. So, let me try to get that situation. First go to the rigid mass. So, we went back to the rigid. Now, you can see that because we are at very high temperature with rigid mass, reflective boundary conditions. So, now what we are going to do is container, let us stop it first, container, and we are going to increase the mass, increase the external pressure so that it will come down. Let us also increase the mass a little bit. So, with that situation, we have external pressure 3.32, a piston has 19.6, we start that. Now, you can see that this piston is coming down and you can see the pressure is gone up to 5.27, is going up, is fluctuating now, and you can see the velocity distribution because temperature is same. So, velocity distribution is not that different. So, now let us look at kinetic energy. Because of fluctuation, now that you have pressure condition, you are seeing that pressure is causing some fluctuation in the temperature, and velocity distribution also is there. Now, let us look at the total energy is also fluctuating because it's now is a fluctuating system, and we have a heat bath. So, now let us say release the heat bath, then you can see what kind of chaos we can create on nonlinearity. Now, you can see the temperature or the total energy is also varying with time, and so now the system is non-equilibrium now with respect to the temperature energy. And now, we are going to look at let us say pressure, which is what we are looking at here. And so, you can see pressure is fluctuating around 6.9 pascals, and that is with the long time tail it will probably settle down, but it has some pressure changes with the temperature. So, if I further increase the temperature, now you can see that the piston will move up slightly and the pressure is gone up to 7.37. So, now we are looking at that. Let us look at the velocity distribution for the blue particles here. You are also looking at so now you can see that because of the pressure there is some softening of the peak, because as it hits the top surface it is blunting the peak because it is essentially reflecting to the particles here. So, this gives you a good understanding about how pressure becomes an important quantity, and it can be calculated, and we are looking at the average pressure values here, and we are changing the volume of the system with the piston as well, and that is creating effects on the pressure and also temperature. So, if you look at, we are essentially following the equation of state, but we are also using the variable of the equation of state. So, we can calculate the pressure term, but remember in this case we are not using Parnello-Rahman situation. We are essentially just calculating the pressure based on the variable coefficient for the kinetic energy provided by all the particles as well as the configurational energy part. So, these two together provide us the full pressure system of a particular pure substance. So, let me stop here. We are now going to look at other properties of interest and see if we can also go using the mean square displacement and find what we call diffusion coefficient, which is connected with the viscosity of the substance. So, we are now starting from pressure, we are now going to get into some of the dynamic properties that we want to calculate in terms of mean square displacement, and also we will look at some of the structural properties looking at radial distribution function. Thank you.